So, hello everybody. Today, our speakers are well-known experts in homological algebra, homotopy theory, and algebraic case theory. Professor Teimuraz-Pirashvili from University of Georgia. So, he shall speak on the category of finite set and the cohomology theory of commutative algebra. So, yes, please.
Thank you for invitation for this talk. We first meet, it was in 1995 or 6. It was almost, I do not know how many, more than 30 years ago. And it was fantastic. Then I discovered you in Batumi. I was so happy. Then
I also very happy to see you again, met you again.
The meeting in Batumi usually are quite wide audience, but I did not expect it to someone from homological algebra, and I was so surprising. You give a wonderful talk. Thank you. And I hope next year we will also see lots of you in Batumi. Hello, Frank. I saw Frank Neumann, my good friend. So.
Hi, Teimuraz.
Okay, let's start it. Hi.
I have to go soon, but I want to say hi.
Okay. Thank you. So, as you already heard, the title of my talk is Category of Finite Sets and Cohomology Theories of Commutative Algebras. The basic results was obtained by 25 years ago, but I still hope that some of the facts will be new for the general audience. Before I will start about main subject, let us fix some notations. So we will fix K to be a fixed commutative ring, and all modules will be over K. In particular, this means that when I write tensor product, and now do we see the text?
Yes, thank you very much.
Thank you, and sorry for, okay. Okay, so that's the title. So that's for the Prague today. By the way, I was only once in Prague, so that somehow I found this wonderful city. And now I'm feeling I'm again in Zlata Praga. But let's start by talk. So as I said, K is a fixed commutative ring. And all modules, if I don't say anything against to this, is considered over K. In particular, tensor product means tensor product over K, and homs means hom over K. And of course, if something is different, I will indicate it explicitly. So as from the title, you will see that we will be consider category of finite sets. Before we go to this concrete category, let's make some general remarks about small categories. If you have the category C, which is assumed to be small, you can consider category of covariant functors, and we call them left C modules and denote this category by C mod. So these are simply covariant functors from C to category modules. I'm sorry. In modules. So these are the covariant factors. I will consider them as the left modules and contravariant factors as right modules. So many facts which you are familiar with usual modules, is true in this generality. In particular, we can define a tensor product of two modules. Like in classical, when your modules are over-ringed, in order to define tensor products, you need to consider two of them. One should be left and another should be right, module over C. So, therefore, in order to define tensor product n times m over C, we must consider C to be right C module. This means n should be contravariant and m should be covariant functor defined over C. And then you can define a tensor product in a similar way as usual tensor product. So it is generated by symbols x times y, where x belongs to evaluation on C, n on C, and evaluation, and y belongs to evaluation of m on C. So the important things, both of them are the same. And C is running all objects of C. And the relations which this generator must satisfy are classes of relation, except maybe this one. Now you have to take account any morphism in category C, and then you will have this relation. Alpha lower star means covariant action of alpha on Y, and alpha upper stars means contravariant. So that's somehow a well-known construction, and it has similar properties as usual tensor product over a ring. And I did not wrote it, but I will assume then you can derive this tensor product, so you can consider not only tensor product, but also Tor groups over small category C. Now I will define one of the main objects for our talk. This is the category of finite sets. So objects are finite sets and morphisms are all maps. It will be convenient to assume then these skeletal, meaning then we restrict ourselves only on sets of this form, 1 to n, when n is anything greater or equal to 0. So somehow for every n, we choose one canonical set with n element, denoted by n lower line. In particular, 0 lower line means empty set, because the set should be started with 1. So these are the objects of my category phi, and morphisms are, as I said, all maps between such sets. I don't think so I will need this one, but I will definitely need this gamma. Gamma is the category now of all finite pointed sets. And pointed means, and the maps should be also pointed. Where is my... It will be convenient to denote by the n in brackets the set which has the elements from 0, 1, etc. It's a bit different from this because I added the 0. And this 0 will be base point always. So that's... So I can assume the objects are such sets when n is non-zero, positive integers, and the morphisms are those morphisms which take 0 to 0. And finally, and maybe I will come with the omega when it will be really needed. Okay. These categories are somehow very classical, and everybody knows lots of things about the finite sets. We are considered functors defined on finite sets, and assume T is such a functor, I will not assume it's covariant or contravariant. It could be one or another one, but I am not, the notion which I will going to define does not matter about the covariancy or contravariancy of T. The factor is called exponential. So it's called the exponential. What? Shit. If it satisfies the following important property, if you take the two sets, x and y, and take the disjoint union of these two sets, the evaluation of T on this set is isomorphic to Tx times Ty. So somehow it is called exponential because it takes the plus two products in this plus in the category of sets, and that's the products in category of modules. Of course, this isomorphism must be functorial on x and y, and moreover, it must be satisfy some coherent conditions. I will not make it precise. I will just say it should be symmetric monoidal factor. So it's somehow very natural conditions. Now, since any finite set is the union of one-point sets, it follows that if I have the exponential factor T, if T is exponential, then the evaluation of T on any finite set N is given by A to tensor N, when A is the evaluation of T at one-point set. That's somehow clear, yeah? So if you take any module A, you can define Tn as A2 times N. But this is defined only on objects. An essential part of functor is behavior on morphisms. Therefore, this functorial structure on T means that the A has an additional structure. And the first question which we ask is, what does it mean? What are this additional structure? The question is quite easy, and it's easy exercise, and it's somehow what it says following this observation. Then, if we consider the exponential factors, covariant exponential factors from finite sets to modules, this category is equivalent to category of commutative algebras. And if you consider contravariant exponential factor, then the category of contravariant exponential factors is equivalent to category of commutative coalgebras. So say somehow I will do. Okay, well, I have to explain why we have this, and it's as I said, it's not difficult, and everybody is invited to find his proof of this fact, but somehow it is more explicitly description of this correspondence. Assume we start with the commutative algebra A, and then you have to construct covariant factor defined on finite sets. It takes the set N A2 tensor N, as we already noticed. The problem is to extend this correspondence on morphisms. And if you take the map F from n elemential set to m elemential sets, then the corresponding action of F on tensor powers is given by this formula. So you take the A1 times AN, and you send it to B times PM when B is defined by this formula. So you just fix J, consider all i's which maps to J, it might be empty. And then you take corresponding a's and you multiply. If the product is empty, then this means BG is 1. So empty product is 1. So, and you see why we need here A to be commutative. Otherwise, this product for non-commutative sets does not make sense, because this sort of the objects you can do only for commutative rings. Conversely, assume you have the exponential factor t. Now I have to introduce commutative algebra. So I take the A to be evaluation of t on 1. This would be my A. Now, to define multiplication, I'm using the unique map which I have from 2-elementary set to 1-elementary set. By functoriality, it induces map from T2 to T1, but T2 is A times A, and T1 is A, so I got the multiplication. And similarly, you have the unique map from empty set to 1, which induces the unit element in A. So then you can verify, then you really get the commutative algebra, and these two constructions are mutually inverse to each other. Okay, here's my question, and the way how investigation was done. We have seen that the category of commutative algebras can be considered as a subcategory of category of left models, namely they correspond to exponential factors. So, but exponential factors are part of the all factors. So, therefore, any factor defined on finite sets, you can think as a generalization of a commutative algebra. Okay, and the question is how far this analogy goes. So, what constructions and notions on commutative algebra you can extend on phi models. This is a big question, and the another question is, if you do this, what for is good? Okay, let me see. First question. Here's a list of the cohomology theories, which usually are defined for commutative algebras, but in fact they have canonical extension to all phi models. They are Derang cohomology, Hochschild homology, cyclic homology, Anderquillian homology, even topological Anderquillian homology. All of them have such an extension. For Derang, I don't know who did this, but for Hochschild and cyclic, it was done by Lodey in his famous paper published in Invenciones. This is why I call this construction by L, because this goes to Lodey. This. So you start with the commutative algebra and then you construct this factor. So this is somehow already in Lodey's paper. Okay, and he also did for cyclic homology and Harrison homology. Harrison homology is the characteristic zero analog of Anderquillian homology. For Anderquillian homology, I proved this fact in my paper, which was published in 2003 in Proceedings of AMS. For topological Anderquillian homology, it was proved even earlier in joint paper with Birgit Richter, and this was published in Topology in 2000. There are interesting lots of open problems. For instance, whether we don't know whether étale cohomology have such an exception. I don't know. Maybe sometimes I doubt whether such exception exists, because it's really a matter of prime ideals, really heart of the commutative algebra. But in contrast to crystalline cohomology, I believe it exists, extension for crystalline cohomology. And somehow, when I accepted this invitation, I thought I will finish my ideas about crystalline cohomology, but I had so many duties here in Tbilisi, so I postponed this project later. Now, why is this good? The point is, category of left modules, unlike to commutative algebras, is abelian with enough injective and projective objects. And so you can use the methods of classical homological algebra without any problems. You don't need simplicial techniques like Quillen developed for commutative algebras and many other tools. And basically, even such, if you take the two objects, you can form direct sum. This is what we are, or even short exact sequence. That's what we are love in abelian categories. But if you take two exponential functors corresponding to commutative algebras, direct sum is not anymore exponential. So even simple construction, you force us to consider functors which not comes from the commutative algebras. As I said, there are lots of homology theories which have such extension, but I decided to talk only on Hochschild homology because the other, for instance, undercurrent homology would take lots of time. And maybe some is not. I decided to skip all these things, and I will consider only about Hochschild homology. Let me I don't know. Something was wrong in my screen. Okay, let me start with the relationship between Hochschild homology and the set. Okay, but this is well known, but let me explain. I will take the smallest simplicial model of set. So this you can think as following diagram. So you have the one elementian set, A0, then the two elementian set, etc. So you have two maps. From two elementian set to one elementian set, there is only one map, and they are definitely same. But here we have these three different maps. And of course, you have the degeneracy maps and so on. So this is somehow simplicial objects, which we would like to consider. So how this works? So in order to define simplicial objects, you have to indicate what sets are in dimension n. So in dimension n, I put this set, which I've already described it as set from 0 to n. It's actually pointed simplicial sets, and the 0 will be pointed. Now the phase maps are given by this nice formula, and SG is given by this formula. For instance, this I have to define this is the 0. To define D1, you take this map, and to define D2, you take these two maps. So they are the phase maps, and it's easy to check, then you really get simplicial objects. And now, why is this geometric realization of this simplicial set with this set? Why? The point is you have to find what are the non-degeneracy simplexes. Of course, 0 is non-degeneracy, 1 is non-degeneracy, this set is non-degeneracy. And every elements here on higher will be degenerate, but it comes from the phase, from these maps. And therefore, you have only two non-degeneracy simplex, one in dimension 0, one in dimension 1. and boundary it makes flow, so that's the set. Okay, now what is the relationship between Hochschild homology and set? The point is, Hochschild homology is usually defined to be, so you have the, assume you have the commutative algebra A and module A. Now, the Hochschild homology is usually defined as the simplicial object, which is A times M. Here you have two maps which are the same and which is given by multiplication. And next you have one more copy of A. And these are A, E, M. So first we multiply these two things. Then you multiply these two things. And you see they are exactly corresponds to these pictures. Having in mind that this functor, which I defined here, sends these sets to the tensor product. And then these correspondence can be easily extended on maps, like we did previously, and then you obtain a functor, which is again defined by L. This is a little bit modification of the previous one when a module is fixed. So, and then in comparing the definition of the Hochschild homology, you'll see that we have the following. First of all, you can define Hochschild homology of a functor by this formula. So what is this? So S1, as I said, is simplicial object given by this picture. And if F is a functor defined on sets, or maybe from gamma to vector spaces, so you can act F degree-wise, and you will get now simplicial module. And from this simplicial module, you make chain complex in a standard way, and this gives the exactly Hochschild cochains when your functor is L. So, and therefore, this formula, which is definition of a
Hochschild.
What do you say? I don't understand. Excuse me.
So I also don't understand. Who have some question? So please continue. I think that's
okay.
Yeah.
Okay, I will continue. Okay, so thank you. So first of all, you define Hochschild homology for any f, any functor f by this formula. So you simply take this set as a simplicial object, simplicial set, apply f degree-wise, you obtain simplicial module, and then take chain complex and define the homology of this chain complex to be Hochschild homology of a functor f. And this observation which we made says that this definition recovers the classical Hochschild homology when your functor comes from the Lodey construction LA. Okay, so this was the observation which was known for many people for many years. Of course, you can somehow generalize this construction. Instead of sets, you can take any simplicial set Y. You can apply f degree-wise, and then you take the, again, chain complex and take homology. And let's call this h of f with respect of y. So when y is certain, you obtain classical Hochschild homology. I considered case when instead S1, I take SD. And I call this higher order Hochschild homology. But investigation by several authors showed that the SD is of course important, but there are other important cases. Namely, for instance, when y is the wedges of S1, like this, or they are the surfaces of G. Okay, so all these are quite important and have lots of application. Okay, so if you look this definition, it looks like very hard to work with because the simplexes in SD grows quite fast, and then you have lots of tensor products and you don't know what you have to do. But you have, when you have the functorial point of view, and as I said, you have lots of tools from the classical homological algebra, and one of them is so-called the Kunet spectral sequence. This is one of the classical tools in homological algebra. So it is described over rings in Cartan-Eilenberg, for instance. And it shows that when the ring is the principal ideal domain, then the spectral sequence degenerates and gives the classical theorem. But this argument works not only for modules over rings, but also modules over small categories. And this gives us following spectral sequence, which is the main tool for, in my opinion, to investigate such objects. In order to use Tor groups, you need to have the covariant and contravariant functors. F is covariant, so that's fine. So this is the covariant. What you have to define now, what is the contravariant part. So y is the space, so I can consider the homology of the space. Homology of space is naturally a commutative quadrant. So this is the quadrant. And by the correspondence between exponential functors and algebras, I said in contravariant, exponential functor corresponds to commutative quadruplet. So I can consider therefore the corresponding exponential functor, which I define it by this. Again, J means Jean-Louis Laudet, because this is still remains one of his works. So now this J of this quadruplet is a now contravariant functor defined on finite sets. So I can take no tensor product. That's the important thing. But before I will do this, let me remark that the homology is graded. Therefore, this functor will be graded, so it has the homogeneous part degree Q. And as I said, it's basically a Kunet spectral sequence, which implies that there is such nice spectral sequence which converges to groups which we look for, and the starting terms looks like horribly because this is F, this is very mysterious construction, and then is Tor over this gamma, which no one worked before, and we don't know how to compute them. And so it looks like horrible. But it has already very important consequence. If you write this for y and y dash, and you have map between y and y dash, it implies functoriality, you have spectral sequence vortices. But if this y to y dash is isomorphism in homology. So these terms will be same, and therefore this part will be same. This implies that the Hochschild homology is independent on the model of a space Y. So we defined it as a simplicial set, but in fact it depends only on space up to homotopy type of space, even homology type of the space. So different models. So for sets, you can take millions of different simplicial models. All of them gives the same result. So the chain complexes will be quite different from the Hochschild's original complexes, but they will introduce same groups. That's the first concept, invariancy of higher order homology on the models. Okay, as I said, in my paper, I considered the case when Y was a sphere, d-dimensional sphere. So. Okay, why I did this? Because the homology of the spheres are very easy, even as a quotient. Because homology of a sphere has only non-trivial terms in 2 dimensions, so you could not find easier than sphere. So therefore, you can simplify the spectral sequence. And for dimensional sphere, it looks like, again, we still have tall groups and so on, but first of all, we have the lots of zeros. Of course, if G is 1, we don't have any, such zeros, but if J is bigger than 1, then we have several lines vanish, which is good. And I will explain what they are later. So, but they are quite, you have to believe me, they are quite simple objects and astonishingly simple, if you think. This is the first observation, but this is not main. Main truth comes from the fact that if K is characteristic 0 case, this spectral sequence collapses. And you obtain decompositions. This odd, and this is for this. Okay, let's come back when D is 1. So and you have to, in this case, we have the classical Hochschild homology, which has decomposition. This reminds you classical Hodge decomposition for Hochschild homology. Let me remind you that such decomposition first was proved by Quillin in 60s in his paper Homology of Commutative Rings, which is still unpublished. And then it was in the 90s was rediscovered by Haber-Schack and Lode. Haber-Schack and Lode both used combinatorial methods. So dimension 2 is quite easy, and it's based basically on this identity. So tensor you can decompose as the sum of symmetric and antisymmetric part. In terms of the idempotence, this means you use these two idempotents which are belonging to group algebra of S2, symmetry group with 2 elements. Next, in degree 3, you still need the idempotents, but now they are like they are very nice idempotents, you see. I do not know how people have managed to write such formulas. And the formula idempotents when n is bigger than 3 are even more complicated. And they are known as Euler's idempotents. So somehow the subject are very classical. Using this idempotence, Jersey-Habenschak and Lodey proved that the classical Hochschild homology has decomposition as piece of n summands. They are written in this way. The summand which corresponds to I1 is so-called Harrison homology or Andre-Kuhn homology. Summand which corresponds to n is related to differential forms. And the other summands are quite mysterious, even today. What I proved is the decomposition which I got using functor homology in terms of Tor groups over gamma, and this classical decomposition, they coincide. Okay. But now this fact has the another consequence. You see, all these groups which I have here appears in the Hodge decomposition. So this means that if you know usual Hochschild homology for which is related to the sets, if you know the usual Hochschild homology together Hodge decomposition, then you know higher order Hochschild homology, at least in odd dimensions. So you see, if you rearrange all these things, you will get this one. So these are the parts which comes from the classical Hodge decomposition of Hochschild homology. So they are related to homology of the set. But it's very strange that exactly these groups with different summation gives the decomposition of the dimensional spheres for all odd D. You see, this summand depends on D. If you change D, then the summands will be changed. Similar phenomena is also true for even D, but now you have to look first decomposition when D is 2. If you know decomposition for D is 2, then you know for everything, for all even D. The only common summand which you have for all of this is this Harrison homology. This appears in all decomposition. And they are somehow, as we say, related to Andre-Kuhn. Now, I expected you to explain these functors which appears, these two functors. And let me do it. But in order to do this, I'm sorry, you have to, we need one more tools from category theory. So, if you consider one, I'm sorry, if you consider 0, 1, 2, this I call R0 or R1, and this map I call R. Similarly, you have in high dimensions, so you have such maps. And these maps are pointed maps. They take 0 to 0, therefore they induce this for any factor t, you get corresponding morphisms from Tn to Tn minus 1. These are the maps induced by this R. And then you take the kernels and take the intersection. What you obtain, you denote this by CRT, and it will be depends on n lower step, lower line. And in this way, you obtain a functor from omega to vector spaces. This is the category. Objects are finite sets. And the morphisms are surjective groups. Okay, so this construction gives a functor. So you started with the T, which is object in gamma module, and you get it the functor defined on omega. So you get such a functor, and there is a little lemma which I call dot-gun theorem for gamma modules, which implies that this is an equivalence of categories. So this means everywhere when I have written gamma, I can simplify and write omega. And you have to think about omega as simplification. I use the gamma because in gamma terms is natural way to assign functor to commutative algebra. To assign functor defined on omega from commutative algebra is a bit messy. Now I would like to define what are these T, G, and T, and lambda T. So omega, as we said, is very easy. So you have the empty set, then you have the 1 point. So you have 1 point set, you have 2 points set. And morphisms you have only in this direction because morphisms must be surjective. So you don't have morphisms from lower to up. So it's very easy. So now we take M, and endomorphism of these objects is, of course, the automatically bijection because the morphism should be surjective, and surjective map from finite set to itself is a bijection. So the endomorphisms are exactly elements of sigma. So if you have functor defined here, so it gives in each stage you obtain a representation. Started now the converse relation, you have a representation of sigma. Then you can define functor, which is so you put M and you put the zeros everywhere, below or above. The only maps which are non-trivial are here, which corresponds to elements of sigma. Okay, so denote this omega module by M tilde. So it's M tilde is everywhere 0 except dimension n when it's as a representation of sigma. So we can apply this now in easiest representation. You take one-dimensional sign representation or one-dimensional trivial representation. So what you obtain in the gamma side, they are exactly this and these functors as they appear in main theorem, which I was talking about. Okay, that's basically all. But since, do I have the few minutes?
Yes, sure. That you have more than 10 minutes or 15 minutes.
Okay.
Yeah.
Okay. So okay, I'm sorry. Now, what I would like to say, I'll just say my words and without writing formulas, is that the material which I presented is about the commutative algebras. And for commutative algebras, finite sets play an important role. And I explained this connection by saying that the exponential functors defined on finite sets are exactly commutative algebras. But this result has deep generalization. First of all, finite sets is an example of something which is called a prop. Prop is generalization of an operand. And like an operand, you can talk about algebras over operand and algebras over props. Algebras over operands are basically algebraic objects. So they are vector spaces. We have some operations which are multilinear and so on and so on. But the algebras over props are more general. So you have not only algebras, which are given by vector space together with operations, but also you could have the co-operations, co-multiplications. So, and for instance, Hopf algebras or Libby algebras or things like this, they are algebras over props but not over operands. So somehow operands are a particular case of props. Now, if you have the operand, so you have the algebras, and there is a way how to define cohomology for this sort of the algebras. First of all, this is the classical work by Quillen, who did this for all sorts of the algebraic objects. But usually they introduce huge complex, which is very hard to use it. And in say 20, it's already 20 years ago. Kapranov defined so-called Koshul operands, and he constructed the nice chain complex for such algebras. But those methods work only in characteristic zero. That's the main restriction. In order to define characteristic PKs, the Koshul duality and the tools which comes is not available, and they have to use again Quillen's machine. But now if you look at algebras over props, for this, even Quillen's theory doesn't work because they are not algebras, so you don't have the free objects and things like this. And therefore, there is a huge area of open objects, mathematical objects, which should have the good cohomology theories, but no one knows how to construct them for general. And the functor homology method, which I was talking to today, might be helpful to solve this problem. That was somehow even my project. And together with the Birgit Richter, we realized that the analogy goes well, for instance, for non-commutative associative algebras. We have
Non-commutative, yes.
Yeah, but non-commutative. But for this, you need to change finite sets, so-called finite non-commutative sets. They are usual sets, but morphisms are different. So morphisms are usual maps together or linear ordering each five of this map. If you have the order of this five, then you can take the product in the formula which was crucial here. In commutative algebra, you can take this product, but not in non-associative algebras. But the if is running of fiber of J, and if you have the order of this fiber, then you can take the product according to this ordering. And so you will get a factor, and you can develop machinery. And we have seen then several cohomology theories related to associative algebra. You can interpret it in this way. So in my opinion, this is quite promising subject, and maybe some of your friends or even you will realize, or anyone, maybe somebody else, but not me, because I am working from completely different objects. Thank you.
So thank you very much, Fiat.
Thank you.
Is there any questions? So I have a question. First up, you consider commutative algebra, but should be work also for graded commutative algebra, right?
Yeah, everything works in graded case as well.
Yeah. And the second question is how to say, so it seems that you define new invariant through the now understood that's a high order Hawking homology that you promise to give a talk when you was in Batumi, but that talk is explain the origin of the higher order Hawking homology. Yes. So there are one thing that's once you define it, you have spectral sequencing, but computation you cannot make any concrete computation or what is
Well, you can, based on this, first of all, as I said, this result in characteristic 0 gives the computation. So if you know usual portion homology, and you know
so
how
that
to
is
decompose.
usual homology. We have some computation. Yes, I at least I know some example how to compute it. But for your case, that's a SD, so that's you have you can compute it also, right? Here, yes, they generate it. And then another question, that's how to say, if the associative algebra is a Frobenius, you have some non-degenerated linear form, right?
Right.
And then you have also the relation between Hawking homology and Hawking cohomology.
Right.
And it's the same for the Harrison.
Yeah, it should be. Yeah, because this is a part of this Hodge decomposition.
Yes, so I am especially, how to say, interested in it because you know that Akadeshvili has a relation between Harrison cohomology and C infinity
types,
algebra.
Yeah.
So do you have some the things related to Hawking cohomology? Because I am interested in the Frobenius case. So you either work with the homology or cohomology, yeah? So then do you expect some relation with the higher order Harrison?
Thank you very much. This is a really nice question. I should admit that I never thought about the Frobenius algebra. This is a really nice class of algebra to look at.
Yes, actually, that is I'm writing a paper on it. So
Oh, very nice. I hope you will send me your copy of it.
December or January, I should send your copy. Yeah. So that extending the reason I report in Batumi. Yeah.
I see.
Yeah. So that's because of you see that's a Poincare algebra. You have the natural right linear form.
I see. Yeah.
Yeah, and then it use something more, but at least that's a very natural. And that is you have the Frobenius property, yeah. And yes, then actually I yes. So I hope that you can discuss more. So I promise to send you our paper once you finish it, yeah.
Yeah, thank you. Thank you.
Thank you very much. Yeah.
Thank you.
Okay, then could you please also send us a slider, copy of slider for?
Sure, I will send it.
Thank you. And is there any more questions? If there's no more question, let us thank the speaker again.
Thank you.